In the previous section, we explored a long descent method. A quicker approach involves using the Pythagorean theorem. We square the initial sum of two squares and then find the remainders when divided by p for the sides of the right triangle. Its squares added up will also be divisible by p. Continuing with case prime 53, Fermat's little theorem and Euler's criterion help us discover that 53 divides 2 raised to 26 plus 1, which equals 8,192 squared plus 1. By squaring and applying the Pythagorean theorem, we get this. So there, we express those values as 53 times a quotient plus or minus a residue. This leads us to find that 53 must divide the sum of the squares of the residues, specifically 2 squared plus 7 squared, which indeed equals 53. So here we have arrived to the solution in just a single step. It's time to switch from expressing things in the form p times q, q for quotient, plus minus r, r for residue, and start using congruences, as they simplify calculations. So saying x is congruent y modulus p is equivalent to say x minus y equals p times k. Given another congruence with the same model p, say w congruence minus z, then x times w is congruent minus y times z modulus p. You can check that's true below. Plus, you could also say that minus x times z is congruent to y times w modulus p. You can verify it yourself just using the same procedure. So it's a handy tool to work with. Let's now consider another case, prime 1801. Fermat's little theorem ensures that that prime divides 5 raised to 1801 minus 1 minus 1. In fact, all bases less than that prime work too, but 5 in particular grants that 5 raised to 450 plus 1 is divisible by that prime. That is, it ensures a sum of 2 squares. All bases less than 5 cannot grant that. The next step would be to rewrite 5 raised to 450 as a square. So instead of 5, we have 5 raised to 225. That is, that number is congruent to minus 824 modulus 1801. So we have the initial sum of 2 squares required. However, working with 5 raised to 225 means dealing with a massive number, a 158 digits long number. But we can simplify the problem, dividing it in a short number of steps as shown above, recombining the base and exponent so as to compute their congruence with the smallest number bigger than 1801. The subsequent step mirrors what we did for prime 53, squaring through the Pythagorean triples. This time, the sum of the squares of the residues doesn't yield the solution right away, but it gets us pretty close. That's because 13 can be easily decomposed as 3 squared plus 2 squared. So the third and final step is to apply Ramagupta's identity, and that gives us the solution. 35 squared plus 24 squared equals 1801. Conclusion. If starting from Fermat's little theorem, given n squared plus 1 equals p times k, where n is bigger than 0 and smaller than p, then squaring the Pythagorean triples method may produce a faster solution only if the absolute value of p minus 2 times n is smaller than the absolute value of n. If instead the initial equation weren't squared plus 1, but n squared plus m squared equals p times j, then the method would be faster if the absolute value of p times s minus 2 times n times m is smaller than the absolute value of n times m for some s. Just remember the Pythagorean triples when squaring the initial sum of two squares, that is, n squared plus 1. Modulus p, the sides of the right triangle are congruent to -2 and some r, respectively. If 2 times n equals r, then you can see that we wouldn't advance any further. You get back to the initial equation. Case prime 557 shows when the method doesn't work, which is pretty common the case, by the way. If the absolute value of 2 times n is bigger than the absolute value of n, then the absolute value of p minus 2 times n is smaller than the absolute value of n. And so 2 squared plus r squared would be a sum of 2 squared smaller than n squared plus 1. Case prime 733 shows when the method works best, when p minus 2 times n is close to 0. It gives you the solution in just a few steps. And at your left, you can see how this applies to primes 53 and 1801, the cases seen before. In the upcoming section, we will explore a completely different approach to infinite descent. This method will serve as a foundation for the techniques we will address in subsequent sections, possibly leading us to Fermat's elusive unpublished infinite descent.